In previous videos, we saw that we could describe a solution in terms of its acidity or basicity based on a value called the pH. We also looked at different types of acids and bases in terms of having strong acids and strong bases and weak acids and weak bases. Now, we know that the pH of a solution is going to be equal to the negative log of the concentration of hydronium. And we know that for a strong acid, the concentration of the acid itself can be treated as being equal to the concentration of hydronium. And that was because a strong acid is going to completely dissociate, completely give up its proton, and produce 1 mole of hydronium for every 1 mole of acid. But this raises the question, how do we deal with weak acids? Because we know that weak acids do not completely dissociate. In fact, they only partially dissociate. So how are we going to go about figuring out what the hydronium concentration is going to be? Well, this is where we have to actually break out the tools that we learned about in chapter 14. Okay, so if we consider a weak acid, I'm just going to pick these general terms here. If we take a weak acid and we add it to water, okay, so the acid's going to be aqueous, water is going to be in the liquid phase. Okay, this weak acid is going to partially dissociate, producing hydronium and whatever that conjugate base is. Okay, and we can describe this process in terms of an equilibrium constant. Okay, this is a heterogeneous equilibrium like we've seen before. So we're going to have the concentrations of hydronium and the conjugate base up top, and the concentration of the acid on the bottom. And like we saw before, we're going to leave out water here. Okay, so this K value is going to describe the degree to which the acid dissociates to form hydronium. Okay, and because we're talking about an acid here, we use the subscript A. Okay, so this is the acid ionization constant. Okay, it's the equilibrium constant for this type of reaction. Okay, and pretty much through the years, scientists have gone and measured the Ka value for a number of different substances. Okay, now, one example here would be the example of hydrofluoric acid. Remember, we said that of all the halogens, fluorine did not produce a strong acid. It's a nasty acid. It's a terrible, dangerous acid. But it's not a strong acid because it does not dissociate completely. So if I take HF and I dissolve it in water, I will form a little bit of hydronium and a little bit of fluoride. And it turns out that the Ka value, okay, for hydrofluoric acid is 7.1 times 10 to the negative fourth, which would be equal to the concentrations, or I should say the equilibrium concentrations of hydronium times fluoride divided by HF. Okay, so let's suppose we have a solution of HF, so we have a 0.010 molar solution of HF, and we want to know what is the pH of this solution. Now remember, we can't just treat the concentration of HF as the concentration of hydronium because, again, HF is a weak acid. It does not completely dissociate and convert to hydronium. So what we need to do here is an equilibrium problem. Okay, so we'll write out the equation. Okay, with the products. And we're going to create an ice table. So we have our initial concentrations, what we expect to be the change in concentration, and then we have the equilibrium concentrations. Okay, so the concentration of HF initially is 0.010. We're not going to worry about water. And initially we're going to say that there is no hydronium. Actually, let's not put slashes there. Let's just put zeros. There's 0 hydronium and 0 fluoride. Now, in order to achieve equilibrium, okay, we're going to have to shift to the right. That's the only direction we can go. So we're going to have to lose some quantity of HF. And whatever that molar quantity is, that's the amount of hydronium that we're going to produce. And that's the amount of fluoride that we're going to produce as well. So that at equilibrium, we expect that the concentration of HF will be equal to 0.010 minus X. The concentration of hydronium will be equal to X, and the concentration of fluoride will be equal to X as well. Okay, so then we can take our equilibrium constant, which we said was equal to 7. Actually, let's even that up there. 7.1 times 10 to the negative 4th. And that's going to be equal to our concentration of hydronium, which we said was X, times the concentration of fluoride, which we also said was X, divided by 0.010 minus X. Okay, now all we have to do here is solve for X, which involves a little bit of algebra. So I'm going to do some of that algebra and we'll kind of skip through that. Okay, so you can see here I've taken the bottom term on the right hand side and I multiplied that against the left hand side of the equation there. And we wind up with an equation that's in the quadratic form. Just got to kind of rearrange it a little bit here. And there we go. We are in the quadratic form where we have 3 coefficients. Okay, we have A, B, and C. And now we just plug this into the quadratic formula. And honestly, I have no problem with you using a quadratic formula calculator. In this day and age, I mean, you might as well. Okay, and when we plug this into our quadratic formula calculator, we wind up with 2 values for X. We get 0.00233, and we get negative 0.00304. Now, looking at these 2 values, we know that these are going, well, whichever one we choose, is going to have to plug in to these values here. Okay, we know that it cannot be a negative number because that would mean our concentration of hydronium would be a negative number. So that rules that out. So this is our answer. Well, kind of. That's the value for X. And we know that the concentration of hydronium equals X, which equals 0.00233. Okay, and that's in units of molarity. Therefore, the pH is going to be equal to the negative log of that value. And the value that I get for the pH is equal to 2.63. And that's the answer. So that's how we deal with trying to calculate the pH of a weak acid system. Now, what about a weak base system? That is going to be the subject of our next video.